Which I want to share with you. That's the quiz number. They are ready to go, and I put them until October 27th. Now, you are, because you are attending, you have the right, if you want extended period, happy to extend it. What do you think? 27th of October, or you go beyond? Date of them. So the date is 27th. So what do you think? 30th, 31st to the Halloween. Okay, let's make it to the Halloween day. Okay, so here it is. You are here, you are the ones who are deciding. Okay, guys. 5 and 6, and they are there already. So now the unique about this is I did not put the answers are open. So when you are done after the 31st, November 1st, I will open the answers. What I have seen, guys, some of you are with wrong answer, changing even I will open the answer. You can see the answer. So we have this quiz 3 and exam 3, covering 5 and 6. Look at the owl. Look at the, if you want to see some worksheets, same thing, look at the PowerPoint. So I will just turn this one off. So we stopped here on this here, and we have so we have n is the principal quantum number n, correct? And if it's 1, like here it is, n1 means L equals 0. L equals 0 means you have the s orbital, which is 1s. Possibility for the that's the second level, second period. You have possibilities, or L equal 1. So you have 2s and 2p. So the second level has 2 orbitals. So it has how many? 2 orbitals. This one has 1 single orbital. Okay. Now 3, have the opportunity to have L equals, so this is 3 here. L equals 0, L equal 1, L equal 2. Then you have the you have here 1, 1, 2. So here it is. So you have the 3s, 2b are here. So let me just take this one here. 3s, 3p, and 3d. Those are 3 ones, 3 orbitals. So now from now on, you will see Those orbitals are coming. Are 3 orbitals. So here we have the number 4. We have 4 orbitals. So if you look at this, those are 4 orbitals, and L will be 0. That's spheric sphere. L equal 1, that's dumbbell. L equal 2, that's another dumbbell. L equal 3, another dumbbell. Now, what makes this is unique? The maximum occupation of the orbital S, so here it is, maximum occupation of S orbitals are 2 electrons. So, maximum of 6 electrons. The d orbitals is 10 electrons. The f orbital, 14 electrons. So, maximum, this is 1. So this is one orbital here. This is S. S is one orbital. P has 3 orbitals. D has 5 orbitals. And F has 7 orbitals. So that will give us the idea you can have only maximum of 2 electrons. You cannot exceed 2 electrons in each orbital. So S will have max 2. So if I look at this, S orbital will have 2 max, 2 electrons max. And the P has 6. Has 10. Have 14. So what does it mean? If you look at this, this is one orbital, correct? This is 3 orbitals. Each orbital, we said maximum of 2. 2 multiplied by 3 makes 6. So 3. This one here, 5. 5 multiplied by 2, maximum of 2, makes 10. This is 7. 7 multiplied by 2. How to build in those electrons into the element, So we have this one here, this method called the head of the arrow and the tail of an arrow. So it means you start with one, the first here. This is 1s. 1s has this, correct? This is 2s. This is 3s, 4s, 5. I mean, n equal 4, n equal 3, n equal 2, n equal 6. That's 6 level, which means can't exceed. We have only 7 periods, so it can't be in the future more than 7. Yes. So if you look like this, the first orbital here, the s orbital, the 1s, maximum of 2 electrons, correct? Second one has 2 orbitals, 2s, 2p. The third one has 3s, 3p, 3d. The fourth one, 4s, 4d, 4f. And then from now on, all those are 4. All those are 4. Now, to fill this one here, we have to look at the rule here. I wanted to make just a piece of paper of this diagram here. So you got this. This is the head of the arrow, 1. Go back. This is the second. Go back. And so on. So you go with all these here. So go back. And so on. So you go back and forth, back and forth. Let me get this one out. So when I have to fill in those orbitals, I start with 1s. Let me see here. So start filling those with 1s. Then 2s, 2p, 3s, 3p, 4s, because I'm going this way here. I'm going this way here. Correct? Those the head of the arrows here. Those are the head of the arrows. So, and it goes up to 6s. Will not go to 6s, but at least we'll have until n equal 4, until the fourth period. N equal 4, that's the fourth period, which is easy. So, let's look at this now. Let's look at some example. Did I put this one in the quiz and the exam? Yes. It's coming in the ACS exam? Yes. This topic will come in the ACS exam. So what's this designations? This is the first quantum number, means that's the period number or number of the principal. This is the period number 1. And the S is, give the shape, correct, angular quantum number, the shape is S sphere, correct? And 1 is number of electrons. So this is for hydrogen. Hydrogen has only 1 electron. Look at this. Hydrogen has 1 electron, correct? So it will have 1s1, correct? Now, if I go for helium, helium has atomic number is 2. Atomic mass is 4. We're not interested in the atomic mass, we're interested in atomic number. So I will have for helium, it is. Now we have to watch. 1 is up, correct? And that's what Pauli says. Maximum 2. And they have to have opposite spin. One will, the electron density around the nucleus clockwise. The other one is the opposite, counterclockwise. So the other one is here. So this is for electron configuration for with orbital diagram. This is for helium. Are you following me here? So if I put the helium like this, like this, this can be in the exam, final exam, or in the quiz. So if I put this both, this is wrong. If I put both of them like this, both of them spinning counterclockwise, that's wrong. According to the Pauling exclusion principle, you have to have maximum of 2 electrons in one orbital, and those they have to have opposite spin. One is up clockwise, one is spinning counterclockwise down. So those are not correct. Now we'll go here and look at this is just magnesium. So we want to see, we have magnesium has 12 electrons. So 12 electrons, I'll start with 1s, maximum of 2, correct? 2s and 2p, that's the second orbital. Maximum 2s2, maximum of p is 6. So 6 plus 2 plus 2, this is 10. The 3s is 2 to make 12. So therefore, the 3s you will see in the next chapter called the 3s2 called, it has a special name called valence electrons. Valence electrons. Now, valence electrons is equal number of the group. So where is magnesium? Magnesium in 2a. So the valence electron has to be 2. Aluminum is in 3. So valence electron of aluminum is 3. Are you following me here? So chlorine in the 7th group. Valence in the 7th group. So the valence electron is 7. So valence electrons here equal number of the group, not the period, the group. So equal number of the group. This is very important. So it's very, very important to know. So you can look at it in the ebook, in the PowerPoints. So, and in the valence electrons are the outermost, the last ones, and electrons. And therefore, exchanging those electrons, giving them away or taking some electrons towards them, that's what the chemical reaction is all about. A chemical reaction is a reaction results in exchange of those valence electrons. When you start exchanging those electrons, valence electrons, which is the number of the group. So how about helium? Not helium. Krypton. What's the valence electrons of krypton? What's the valence of krypton? Krypton where? 8A, correct? Group number 8. So the valence electrons of krypton is 8. All of them except helium, because helium has only 2. Helium has only 2. Does not have, but all of them, the rest of the group 8, they have valence electrons 8. Are you following me here? So the number of the group is the number of the valence electrons. So let's look at this here. Now we have 12. We have accommodated 12 here. We have accommodated 12. How we accommodate them? So 1s2 maximum. That's the second. 2. That's the second orbital, the second period. 2s, 2s2, 2p6. This is 8, and 2 here 10. This is the last 2 is the valence electrons, 3s2. So that's the way we can. So now we can abbreviate this by looking at this one here. This one here. This one is nothing less than just neon. This one is neon. So we can say neon, and so we can take this one here. This is neon because it comes up to here, 10, and 3s2. That's abbreviated. So how we do this? Well, it turns out to be, if we look at the second one, let's look at this. Look at this periodic table. So what's happened is, if you look at this, so what's happened is, in order to look at the electrons, so you look at this. So here it is. This is magnesium. Here is magnesium, correct? So here it is. Let me see. Here is magnesium. So you go all the way the period of magnesium to the last one, correct? This is the last period here. You go one period up. You go one period up, which is neon. Number of electrons, atomic number is 10. 10. Atomic number has nothing to do with the valence electron. Valence electrons equal number of the group. This is 8, so therefore 8a, so this is 8. This one here, whenever it's like, I have barium here, correct? What's the abbreviated electron configuration for barium? I go all the way here. Radon, correct? Then I go up one period up, that's xenon. So xenon, correct? And then I look at the barium is where? In the second one, correct? The second one, and it is in the 1, 2, 3, 4, 5, 6. So xenon and 6s2. So you see how nice you can do all those without any problem. Xenon, and then 6, this is in the period 6, and then S2 because this is the carry the valence electrons number of the group. This is group 2. So now Hund is telling us here, this one here is about the 3D, 4D, 5D, all those how they are. You can build those. But before we go further, we have to look at this. This is the second rule. So first rule is Pauling. Pauling says maximum of an orbital to carry out maximum electrons. The maximum of electrons are 2 electrons. And second condition for Pauling, they have to have opposite what spin. One's up, the second one is down. Now Hund is saying if you have those electrons coming and you want to fill them, they have to come and fill parallel to each other singly. They have to enter singly the orbital and parallel to each other. Like you have a dot and you have a space shuttle, correct? You cannot imagine those space shuttles are electrons. You cannot put them one near the other. They have to come singly first, one at a time, and then their position has to be parallel to each other. So the nose of this space shuttle has to be up. The tail has to be the other side. Are you following me here? So they have to come and enter singly. So all of them, their heads, the noses are up front, their tails in the back. So that's what Hund says. Says when those electrons are coming and will filling those orbitals, they have to come and enter those orbitals singly. And they have to be parallel to each other. Parallel means they have to have the same spin. Look at nitrogen here. Correct? Nitrogen is, what's the nitrogen? What's the nitrogen atomic number? What's the atomic number for nitrogen? Atomic number? Come on, guys. How much? 7. Atomic number is 7. So, okay, so 7. And it is in nitrogen in what? In group 3, 4, 5, 5A. So nitrogen 5A. Correct? So we have nitrogen is 1s2, 2s2. Correct? And then 2p, and we have to watch. So 4, and then we have to have what? 3. So it's nitrogen, nothing 5A. Group 5A, yeah. This means it will have 5 valence electrons, yeah. So from here, it will have nitrogen. Nitrogen has, correct, it's 5A, and the valence electrons, because it's 5A, 5 valence electrons, correct? So it's in if you look at this, it is in period number 2, correct? So period number 2, so we have 1s2, 2s2, 2p, whatever is will be 3, correct? Why is 3? Because it has to have maximum 7. It has 5 valence electrons, correct? But the atomic number is 7, so it has 7. So 2, 2, 2, this makes 7. So when you enter them, first you fill one S. According to Pauling, maximum accumulation will be 2 maximum with opposite spin. One is up, one is down. Then you fill the 2S. One opposite with each other in spin. Then when it comes to this, to the 2P, you have to watch for this. So you have to watch for this because now you have to, until now we have here Pauling rule. Here we have Hund's. Here is Hund rule. And here is Pauling. Everybody's following me here? So Pauling will tell you maximum 2, and they have to be parallel to, opposite spin. Once you have to enter them singly, and parallel to each other means they have the same spin. So one is up, one is up, one is up. Those three are all of them up. They have the same spin. But how about if I did this one here? One of them, I said, well, I'll take the other one. I filled this one here too. Here it is. I filled this one too. So this is wrong according to Hunt rules. You cannot. First, you have to you enter them singly, and they have to have the same spin parallel to each other. So this is wrong. This is correct, and this is called Hund's rule. So we have two types of matter here. We have the matter itself called paramagnetic, means the matter is attracted to what? To the magnetic field. So paramagnetic means this element is attracted to what? To the paramagnetic, to the electromagnetic field. Why? Because it has unpaired. Look at this. Those electrons are up, the same spin, and parallel to each other. The diamagnetic one, all electrons are paired. See here? All electrons are opposite to each other, so they don't attract. Magnetic field. Iron, if you look at iron is attracted to magnetic field, correct? You did this one experiment in the lab. Iron is magnetic. So oxygen, believe it or not, as a gas, and you bring it to a magnetic field, it will be attracted to the magnetic field. This is paramagnetic. So the paramagnetic, those are attracted to magnetic field. So those are attracted to this attraction. So this is attraction. And the other one is repulsion. Here you have a repulsion. They are not magnetic. They are repelling the magnetic field. If they have all their electrons inside the orbitals are paired with each other with opposite spin, but here they have the same spin, correct? So what you can tell me about we took just nitrogen, correct? Is nitrogen is paramagnetic or diamagnetic? Look at here. Is nitrogen is paramagnetic or diamagnetic? It's para or di? It's paramagnetic. Why? Because you have all those here. Look at this. Those are parallel to each other. They are not filled. Correct? Those unpaired. So nitrogen as an atom is paramagnetic. Oxygen is paramagnetic as well. So you can see as an atom. So this is paramagnetic. So because you have those unpaired electrons. So let's go and look at this. Here will tell you how about the when you fill those are the host orbital for valence electrons. So group 1A, their valence electrons is is this. Group 2A, their valence electrons is this. Group 3A, their valence electron is this. 4A, when I say 4, you can add 10 to it, it will be 14, correct? 15, 5 plus 10, 5A, or add 10 to it is 15. 6, add 10 to it is 16. So the valence electrons is this. And 7 add to it is 17. And 8 add to it, 10 will be 18. And this is the valence electrons hosting orbital. You can just write them in a piece of paper so you can look at this. Now, the only unique about this, the transitional elements, they are very unique. Like group 1 here, you start from here, correct? So they have D1. This is D5, correct? Of course, S is there too. This is T10. So you can tell about this when it comes to valence electron hosting orbitals, correct? So here it is, guys. Now, the electron configuration of cations and anions. What is cation and what's anion? Somebody will tell me. What is cation? An atom. Cation is an atom that had lost electrons, correct? And therefore it appears positive. It appears positive. Anion is an atom that's gained electrons that will appear what? Negative. So the metals tend to be cations most of the time, but there is non-metal that can be cation as well. So this metal here, cation. This is cation. This is another cation. So it means because it has one positive, so it lost what? One electron. This is two positive, so it lost how many? 2 electrons. Right? This is 3 positive, so it means it lost 3 electrons are gone out. Right? But the neutral atom, you can see here this neon is 10. Correct? So you can see sodium is 13, 10 plus 1 is 13. You look at the argon, argon is what, 18, correct? Calcium is 20. This is 20, correct? This is 18, sorry. This is 18. This is 18 here, argon. So calcium is, atomic number is 20. So this is 18 plus 2. And aluminum is, this is 10 plus 3 makes 13. Aluminum is atomic. If you look, it has total of 13 electrons. Now, if you look at what is the electron configuration of those elements. Okay? So we have, let's look here. The color. This sodium here had lost 1 electron, correct? What is this one here? So it will be neon, correct? Because it has lost 1 electron, will be 3s. What's the 3s? How many electrons 3s? Correct? 3s because this sodium had lost 1 electron to be 1 positive cation. So this is 0 here, so we can take this one out because there's no orbital 3s 0. So this one will be just Ne. Okay. How about this one here? It lost 3 electrons, so this one will be gone. This one will be gone. So Al3 will be what? Will be again neon. So Na plus and aluminum 3, aluminum 3 plus, called isoelectronic. isoelectronic means they have the same electron configuration, which is neon, correct? Because you took all this electron, the three ones, come up to be neon. Took one of them, you came up to be neon. So this one here and this one here, they have the same identical electron configuration. They are set. 'Fluorine by itself, atom, this is the fluorine. Six. Now, sodium. So they have the same isoelectronic structure. How about oxygen? Oxygen O2. So it will gain 2 electrons. And if you look here, you have 4 at the end. Add to it to 6. So that will be neon. So all those 3 here, beside aluminum and sodium, called isoelectronic um, electron configuration. So they have the same configuration. So now, if you look at this, that's what I mentioned a couple of minutes. So we call them isoelectronic. It's coming as a concept question, no calculation. That's what I tell you. Give you some couple elements. Which one is isoelectronic? So you know they have the same. The ones they have the same, they are the same. Sodium. Isoelectronic. Hydrogen, hydride negative. Atomic number is 2 and atomic mass is 2 electrons. So the structure of this is 1s2, 4 for this as well. So helium and H minus have the same electron configuration. So now this is the same thing here with the same thing we did. So you have iron. This is the neutral one. That's the neutral one. Now, if you have iron 2, then you have to lose 2. So the 2 will come first from the s orbital. So the s orbital is out. If you have 3, then will be you come and take it from the 6 here. So that will be electron configuration for iron 2. This is electron iron 3. same thing with manganese. This is the neutral one here, Mn2. So you lost 2. So then the 2 here is taken away. So that will be 4s0. So this is the nucleus, correct? But at least you get the idea. Now, the the orbitals close to the nucleus, maybe N1 and maybe N2, those are shield, called what? They are shield. So it means the positive charge of the nucleus is being shielded with those electrons close to it. So the nucleus does not feel, you go higher and higher and higher. So the nucleus does not feel the attraction between the positive protons and the negative electrons. They are far away, and they are shielded by the two filled orbitals of the first one and the second one. So those are called here, let me just, so those are here, this area here are shield. It's acting like real shield. So they're preventing the positive, this is positive here, that's protons. Don't worry about neutrons. Neutrons, they have no charge. Positive, and all those here, they have negative charge. All those orbitals, they have electrons, negative charge. But then maybe 3, 4, they can feel the negative charges. They can feel the attraction of this positive nucleus. But when you go higher, they don't feel nothing. Or if you look, when I say, if you have a radioactive material, it's very large. So it's by itself radiated. So because nucleus has no way, electrons are given away by themselves naturally. You don't have to do any experiment with them. So therefore, here, if you look at this shielding here, it has a formula. We have the core. The core is the rest of the electrons. And the atomic number is 11. Since it is in first group, 1A, correct? 1A, it has 1 valence electrons. So 4, that's the rest of the electrons. Atomic, that's the whole. We subtract those two, 11, that's the atomic number. Atomic number, 10 minus 11 minus 10 equal to 1. So really the nucleus does not that's what we call the effective nuclear charge. So the positive charge, it feels only 1 electron. Are you following me? Only 1 electron. All the rest is not felt by the nucleus. Same thing with magnesium. Atomic number is 12, and the core is 10. Thus the core is in, this is the noble gas. This is noble gas, neon or argon or whatever. So 12 minus 10 is 2. So let's feel the whole 12 electrons. It feels really just only two negative particles of electrons. Does not feel all of them. And that's because of the fact of the shielding of the core. If you look at the neon, if you look on nitrogen, let's look at nitrogen. Nitrogen was a 3, so nitrogen goes all the way to argon, neon. This is the electron configuration of nitrogen. 3, So this is called core shield, core, or called a shield. So this is a shield that's preventing the nucleus to interact or having influence on the rest of electrons. So what's really is influencing the whole thing is the 3s1, this one here. So the nucleus have more effect on the first one, and the other ones are just as a shield. So that's the reason we call it shield. So then effective, this is the way it is. So when you got this one, effective nuclear charge, if you go, this is the, you go down here, is the opposite of the radius. So decreasing. Because it's the opposite of the radius, decreases. And when you go from left to right, this is increases. Okay, guys, so I wanted to memorize this because that will help you. Nuclear charge going to left to right, so increasing, going up and down is decreases. So you can see all those here, relationship between contents of the periodic table. So here, atomic radius. So atomic radius, the opposite. So here it is. Atomic radius from left to right, the periodic table from within the period. This is the period here. Period, correct? Left to right, atomic radius, AR, will, you can see the size of them, they are decreasing, correct? Here, look at the fluorine. See how small fluorine is, how big lithium is? So decreases. So they are, the atomic radius decreases. But if you go from within the group, this is the group here. This is the group here, guys. From top of the group to the bottom of the group. So you'll see atomic radius is increases. As I said, you have to get the last it is, guys. Get you the last one here and print it out in front of you so you can visualize what is really going on. So atomic radius is a resistance. I'll show you how this means. So atomic radius from top to the bottom increases, it decreases. Get the pictures this way. The compound we'll see later on. The lithium has bigger radius, and the fluorine smaller radius. Now, when lithium is giving away its electron to be cation, correct? Then you get the opposite. Lithium will be shrinking in size, and the fluorine is taking 1 electron will increase. So this one is increase, and this one will be decrease. So you can see the picture here. One is decreasing, one is increasing. But in the real life, without any reaction, without any interaction, the atomic radius at the beginning is huge. When you go within the period, it decreases. But then when it's donating 1 electron, the electron will be taken by the fluorine. It will be bigger now. The lithium will shrink, right? And that's what it says here. That's what it says here. Okay, so this is the definition of atomic radius. Atomic radius is a distance between 2 adjacent nuclei. So I have here, this nucleus here, A. This is nucleus B. So the radius is this one here. The radius is this one here. The radius is from this to this, from this to this. That's the adjacent, correct? Adjacent, between adjacent atoms, that will be the distance between them will be atomic atomic radius. So we can, this is give you the diameter here. So you don't have to worry about this, but at least you will know the definition of atomic radius. So here, atomic radius is the opposite of what? Of the normal atomic radius without ions. Without ions, you can see it is. You can see here, the number is there. When you go this way here, correct? So if you go this way here, the atomic radius colored red and blue, valence atom brown. So you can see this is the opposite of in Biko, the opposite. So you can see the whenever the lithium by itself is big, when it comes to giving away its electron, it will shrink. Correct? It will shrink. And this one here will increase. So from 60 to 136. So, and here it is, another isoelectronic species. What do we mean by isoelectronic? Isoelectronic are cation or anion or atoms. They have the same electron configuration. They have the same electron configuration. Is this coming in the final exam? Yes. Is this coming in the quiz 3 and exam 3? Yes. We have to know the electron configuration. If they are the same, then they share the same thing. But it does not mean they share the same physical or chemical properties. But isoelectronic means they share the same what we call it, the same the electron configuration. Yes, thank you. So now we did the atomic radius, we did the effective nuclear charge. Now we are doing ionization energy. Well, the ionization energy is defined as amount of energy needed, correct, to pull out. We are pulling one electrons out of its atom in the gaseous phase. In the gas phase, you are pulling out 1 electron, correct? So if I have, let's look at this. I have helium, for example. Let's look at this and tell me what you think. This is helium, correct? Helium has 2 electrons, and the electron configuration is 2s2, correct? So helium here will come and I'm pulling 1 electron, so helium positive, correct? 1 positive, and I'm pulling 1 electron. This is the first ionization. This is I1. Then I take the second one, a positive here, pull further 1, that will be H, helium, 2 positive, plus I'm pulling another electron. This pen is, so here it is, helium, goes to helium plus one electron, and helium plus helium, two pluses, plus one electron. So guys, this is one electron. So this is Hi1. This is I2. Which one is higher? I1 or I2? First ionization energy or the second one? Let's visualize this. This is helium, and it has, correct? This is the nucleus of helium, and it has, this is the first orbital. So it has, let me just put this one here. All right, it has, one is here, one is here. Okay, so I'm taking first this one from the first orbital, and then taking this one. Which one will I have to put a lot of energy? The one closer to the nucleus, because that's positive, will be more attracted to the electron, correct? So therefore, this one here is you need tremendous of energy to take it out. Why? Because it's very, very close to the nucleus. The other one is far away from the nucleus, so it's easy to be kicked out. You can take it easy out. But the second one, you need a lot of energy to take it out. So therefore, if you look at this, what do you think about this? This is the third one, correct? Always the last one is the most, the most difficult one to take, because it's very close to, so this one here is, so the last one always difficult to take, correct? First one is easy, and the second one is moderate. Third one, it takes from you a lot of energy to take it out, because it's very, very close to the nucleus, and nucleus tries to hold it and not to give it away. So you have to put a lot of energy to take it out. And that's what it says here. That's what it says here. So this one is the largest, correct? Okay. This is just ionization energy trend. Now, can you remember the trend? Somebody will tell me. This is period, correct? Left to right. This is group, top to bottom. So tell me what's happened to ionization energy. Amount of energy needed, pull out an electron from a gaseous atom, right? Pull out. So what do you think? Always, yes, always remember the ionization energy, effective charge, the electron affinity, all those are opposite to the radius. The larger the radius, the smaller the ionization energy, correct? The larger the radius, so the electrons far away, that's ionization energy you don't need. So very, very small energy you need to put in to get them out. So the radius goes from top, increase the radius. So here, AR, atomic radius goes up. This is the key. All of them opposite to AR, to atomic radius. So therefore, IE, ionization energy, correct? Here will go down. Ionization energy will go down. Electron affinity will go down. Are you following me here? Electronegativity will go down. So now how many? And the effective charge here, will go down. Now, can you see the picture here? Which one is the exception for the rule? Is this one here. This one is an exception for the rule. This one here, this is an exception. That's always opposite to all the rest of the physical properties of the so atomic radius from the top to the bottom will increase. However, the ionization energy, electron affinity, electron negativity, then effective nuclear charge, they will go down, correct? Now, here, if you go from this within the period, the AR, what? It will go down, correct? So it will go down. Then what do you think? Then all the rest, i.e., ionization energy, correct? Electron affinity, and electronegativity, and effective nuclear charge, although the rest of the thing, they will go up. Why? The radius is going down. They have to go up. Right? They go up. Are you following me here? So they are the opposite, and that's what we have there. So that's what we have there. So here is just give you the how those atomic radius are done. So how the distribution of ionization energy. And here is electron affinity. What is difference between electron affinity and ionization energy? Well, ionization energy, you are pulling electrons out of a neutral atom in gaseous phase. The electron affinity, you are not pulling, you are taking in electrons from adjacent atom in the gaseous phase, the opposite. But then the behavior of them is the same thing. The behavior is the same thing, correct? So that's the difference between them. And electron affinity, that's the same, is give you how they increase from left to right, they decrease from the top to the bottom. And here is the key. I want you to really have some time with this, because this is what we just talked about, right? That's what we have talked about. Now, the any question? That's what conclude chapter 6. I will go just a little bit with chapter 7.